you can put this paper in from a Hazelman group and they published not just this paper, but a lot of the other papers showing that using a micropipette tip, putting intact with the cells and slowly drag away this micropipette tip, they can stimulate the growth of the axon from these neurons. They'll further show that if they're increasing the applied force, they can increasing the growth rate of the neurons. And that's a big error bar here because you see the two different cells. But anyway, this showing very surprising and very interesting results that mechanical tension indeed have the effect on the growth of axons. But if we looking at some of the theoretical papers, some of them was already predict that the growth of the cells, especially the growth of the neurons, is already involved in tension from this intrinsic growth of the neurons. So when a neuronal cell grows, usually they're going to find some extracellular matrix to attach the tip of the axon onto the substrate, and then pulling them. By doing that, they create the tension to help the extension of these axons. And Lambros published a paper in Nature which showing that this is not just in theory, it's actually happened in the experiment, that they put a micropipette on the side of the cells and they let the cell grow spontaneously. And then when the cell grows, they can see that the cell apply a tension, a pulling force on the micropipette. And then now the question in this research, we want to ask ourselves, instead of using this very bulky and slow method, can we develop a method to effectively, using mechanical tension to initiate the growth of axon, not just from one cell, but from multiple cells? And then we ask the second question is how fundamentally that happen, how the tension can affect on the growth of the neurons. So let's go to solve the first questions. So we're looking at the methods that people use to apply stretch on the cell. The two typical ones, one of them I just described you using the micropipette. The second one is the optical tweezer. You can shine laser using a bead on the cells, and now moving the bead away, you can stretch the cell by using this optical tweezer. But we don't want to use that because, oh.
Yay!
I think you were just checking if we were still paying attention. Let's practice. We are.
Okay. So let's go back to this. Okay, so but these methods is very low throughput because you can see right away that the tension applied on the cell this in the serial approach, and then only one cell is initiated from this method at one time. So the way we want to do is differently. We want to simultaneously apply tension on multiple cells at the same time to initiate the growth of the neurons. And so the solution for that is inspired by the method named micropipette aspirations. So this is the common method in biomechanical community. Scientists use this a lot to investigate how stiff the cellular membrane is by applying a vacuum using a glass micropipette put in the cell, using a vacuum to suck the cell into this channel. And so looking at this portion, they can see how stiff the cell is, and then they can calculate the elastic modulus of the cells. So the way we want to do that is we develop a microfluidic channels that instead of using this bulky micropipette, we use the microfluidic channels, apply vacuum and suck the cell into this vacuum, and by applying the stress, we can initiate the neurites from the cells. But the beauty of the microfluidic device...
Explain your picture to me. You've got the first part, the green part.
Okay.
The first one makes sense. You've got a cell membrane and you're applying a tension via a pressure or a lack of a pressure differential. But now all of a sudden you've got a piece of stuff just wandering off with presumably no tensile force on it.
Yes,
Is that what you intend to?
exactly?
to tell me? Good,
So we
I've
try
understood.
to apply vacuum suction here, and
Once
then-
it starts, it can continue without a tensile force.
Is that, yeah, exactly. Okay.
Okay.
But the beauty of the microfluidic device is we can make an array of microchannel instead of one channel, and now we can do that for multiple cells and initiate the multiple neurites at the same time. So we use the microfluidic schematic, we use the microfluidic structure that's similar to the Taylor in Nature method 2005, which have two chambers. But instead, two of them all have the, but we have one of them is a vacuum chamber that we can apply the vacuum to suck the cell into the microchannels. And the first chamber we put the cell in and put a medium growth in to provide nutrition to the cell alive. And that's adapted from this paper and the micropipette aspiration paper I just described. And this is a real image that shows you the camera image of the microfluidic device that has one vacuum tube plugged into the vacuum chamber and the growth chamber with the medium growth. And now this is a camera, this is the microscopic image showing you the connecting vacuum, the connecting channel between the two chambers. And the result was wonderful. So you can see that by applying the vacuum into this bundle of cells, we can suck the cell into that and then let the cell growing the very long neurites out from the cell body. And it has a similar structure. It has the typical structure of the axon in a spontaneous growth neurons at this growth cone with a cup-like shape. So it is a very high throughput method that we can able to initiate the growth from multiple cells at the same time. But we can also do the control experiment to show you an apparent effect of the vacuum onto the cells. So divide this vacuum chamber into two chambers. One is vacuum, one we don't apply vacuum. And you can see that the cell seeing the vacuum was indeed grow faster than this cell that without no vacuum after 12 hours of the incubations. So now it's a clear evidence that the vacuum and the tension can initiate the growth of the cells. But now we come to the second question. Why this happened and how this tension can affect on the growth, on the development of the neuronal cells. So to answer that question, we need to look at the microscopic image of the axons. The axon in the neurons is a collection of the microtubules. So when it extends, it actually, what happened is the microtubule keep polymerizing, and it keep collecting and polymerizing at the tip of the axons. But at the very tip of the axon, they call it a lamellar polymer. Now there's a lot of actin filament, and the membrane and actin filament now apparently form a compressive force in the microtubules. And experimentally, people also see that this microtubule has a buccal structure, that is proving that this is always under the compressions. Now, this compression from the actin filament, which is the green one here, will form a very high energy barrier to inhibit the polymerization of the microtubule, or the red ones. So that's the key for our model to explain this effect. That is the compressive force of the actin and the cellular membrane will inhibit this polymerization of the microtubules. So basically by creating an energy barrier, F times delta. With delta is the length of a tubular monomer. So it's similar to the diffusion model, that if you have an energy barrier, which is the activation energy, if you have it higher, then you slow down the diffusion process. And it's very easy to see that if you imagine that the cellular structure like a tent, which has the membrane and the actin like this curvy fluid here, and then the microtubule is like a spring. So when it's in the normal condition, now you have the tension from the cellular membrane and the actin filament push a force on the microtubule, and that's why it push this one under the compression. But if you apply a tension on it, you can stretch the microtubule out, and now you reduce the compressive force on the microtubule. That's the mechanism why we can initiate we can reduce the energy barrier and speed up the growth process of the neurites. We can do the calculation to calculate the new compressive force, which is NF is equal to the initial force minus this term. Kmem is the spin constant of the membrane and the acting filament. Kmic is the microtubule spin constant. So you can see that when you increase the applied tension, you can reduce the compressive force. We also want to calculate the growth rate or the dynamics of these polymerizations. So the growth rate of that is equal to the rate